All right, so you might want to take some notes. Let me just open this up and take it out. So I'm not reading over, kind of funny. Okay, so let me just see if it came up. Oh, there it is. I think this is my thing. Yes, oh good, okay. That's good. All right, so I'm gonna download this and I'm gonna bring it into Classroom. All right, so let me share my screen. Okay, Classroom. And area lessons. Here we go. Lessons. Okay. So let me add a file. Browse. Download.
It's probably the first one at 10:10 a.m.
Yeah. Just gotta wait for that little wheel to stop turning.
Oh.
Vital, do you have children?
No.
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 That's why you can concentrate at home.
It's true. Yes, we very quiet. And we have like space, so we're, my husband has his office and I have
Right.
the basement.
Right. Okay. I'm trying to make this a little bigger. Okay. Okay.
And this would be for 5th grade, right?
Yes, this is definitely 5th grade. All right. So it says all the work we've done with the second series of the constructive triangles has opened up to us 2 avenues of work: the study of the relationship of lines and related figures, and the study of area. Okay. And I would strongly recommend that you put this on your reading list, The Advanced Montessori Method, Volume 2.
Okay.
I would read the whole book because it is absolutely fabulous. It'll give you an amazing understanding of the elementary curriculum, of why it was designed the way it was, how the cosmic education piece ties into it. I don't know if you even heard that term yet, of
I
cosmic.
think you mentioned it.
Right. So this book is a critical reading for you. It's not the easiest read. This book is based on, it's actually a transcript
Okay.
of Maria Montessori's speech when she came to visit to the United States for the first time.
Okay.
But it's a wonderful book. It'll just really show you the spirit of Montessori and how it shows up in the curriculum. So I really strongly urge that you read this book. Okay, so for the concept of equivalent figures, we have this other material that we're going to look at today, right? Okay, so the materials are 20 metal insets of equivalent figures, and you can group these into families. So I think I pretty much have a video for each one of these that'll show you how to use them. So the first one, they call inset 1, is from the triangle to the rectangle. Then we have from the rhombus to the rectangle. So you see, we're always going back to the rectangle because that's what we know, right?
Yeah.
That's the defined area. From the parallelogram to the rectangle, from the trapezoid to the rectangle, from the regular polygon to the rectangle, from the decagon to the rectangle. And then that last one that you can't see says the theorem of Pythagoras, which we already looked at, okay?
Okay.
So this kind of gives you an introduction. Okay. All right, so that, I can now put this aside and all right. Let me see. Okay, so I want to show you. Let me stop sharing here. Oh, shoot. Sorry, Michaela's trying to get in. There we go. Okay. All right. I'm going to plug in my other computer so you can see. Hello, I'm sorry about that. I don't know how long you were waiting.
It's okay.
All right. Didn't mean to ignore you.
It's all good.
Good morning.
My other, there we go. Is this switching?
Miriam said that she's running late.
Yes. Okay. So, I want to show you I have here a, so in my album, I actually have these little envelopes. Okay, and this one is for inset number 1. And I guess I made these when I was in my training. And you'll see them in the video, but I wanted to show you. So this is from the triangle to the rectangle. So I'm not sure right now how this will go. Maybe it's like this. Just want to give you an idea of how this works. So right now I'm not sure. So we're going to watch the video. I don't remember, but in my album, I actually have these little cutouts. I have envelopes for each of the insets, which is quite a nice thing to have. And the students are going to make their own as they watch the videos. Okay. All right. So they're going to make their own. Okay. All right. Okay. Okay, so let's take a look at the first video. Again, I'm going to share my screen and we are going to go for triangle to rectangle right here. Okay.
This presentation is showing the equivalence between a triangle and a rectangle, and it's the first in the series of presentations using the metal insets of equivalence. For this series of presentations, we'll be going through 4 steps, repeating each of the steps as we go through the process, verifying the equivalence between these figures. Step 1 is to name the figures. This is a triangle, this is a rectangle. That was step 1. Step 2 is showing the sensorial equivalence of the figures.
That was showing the sensorial equivalence. So they're going to go through, first they do it sensorially, then they do it mathematically. All right, so that's the pattern. Now again, she's doing it in silence.
The pieces of the triangle fill the frame of the rectangle.
So I think the way I would do it differently, so this is obviously a primary or lower elementary presentation.
Yeah.
Working with upper elementary students, I would do this a little differently, and I would invite them to try it. Do you think that we could turn this triangle into a rectangle? And I would pass around this thing and let kids try it. That's how I would involve them,
Mhm.
instead of just doing it for them.
The pieces for the rectangle fill the frame of the triangle. That was step 2. Step 3 is naming the lines in the figures.
Okay. So now what we have is we have the rectangle length and width, right?
Mhm.
And in the triangle, we have the base and the height. And we're going to see the connection between these.
This is the base of the triangle. This is the base of the rectangle.
You see they're equal.
This is the height of the triangle. It's the perpendicular distance from the base to the opposite vertex. This is the height of the rectangle. Base of the triangle, base of the rectangle. Height of the triangle, height of the rectangle.
Okay, so at this point, I don't know that she's going to do any writing, but I will show you the writing after we look at this. Because again, she's not doing an upper elementary presentation. She's doing a younger child presentation. So at this point, we're going to make the connection that the base of the triangle is equal to the width of the rectangle, right? So area of the rectangle is length times width. So we can make that substitution, right? And then we're going to make the connection that the height of the triangle is actually twice the height of the rectangle, or twice the length, right? Twice the length. So let's keep going and see how she does it.
That was step 3. Step 4, this is where we make a statement of the relationship between the lines in these two equivalent figures. The base of the triangle is equal to the base of the rectangle. The height of the triangle is twice the height of the rectangle. Or we can talk about the rectangle's lines relative to the triangle. The base of the rectangle is equal to the base of the triangle. The height of the rectangle is equal to half the height of the triangle.
Okay. So, so let's now, I'm going to open up a document so that we can take a look at what you would write down for the students, because you're now talking about 5th grade.
Yeah.
And they can handle a lot. Okay. So we have the rectangle, and then we have the triangle. Okay, so what did we learn about the relationships here? So we know that the area of a rectangle is equal to the length times the width. It's equal to the length times the width. All right, and of course, you would ask the children, who knows what's the formula for the area of a rectangle? And if they don't know, just go back to multiplication. Show them a multiplication matrix, and they'll see right away that the area is simply the length times the width. Okay, so what else have we learned about the relationship between these things? We can say that the base of the triangle equals the width of the rectangle, right? We showed that. And again, I'll share this on Google Classroom, so you don't necessarily need to copy it, but so the base of the triangle is the width of the equals the width of the rectangle. And we also showed that the height of the rectangle equals half of the height of the triangle, right?
Yeah.
So if we now want to go ahead and write the formula for the area of a triangle, it's simply, we know it has the same area as the rectangle because we saw that they are equivalent. The areas are equivalent. So if I were to take the area and just substitute the values, well, the length, I'm going to say the height of the rectangle equals half the height of the triangle, which equals to the length, right? That was the other dimension of the rectangle, right?
Yeah. Would it make more sense to say the area of the rectangle is base times height?
Okay, then we're going to get there.
Okay.
Right? We're going to get there. Yes, we're going to get there in a minute. Okay, so now, so obviously you're going to present this the way that it makes sense to you.
Right.
Okay, this is how I'm thinking about it, but we all think differently. So I'm going to just go ahead and plug in for length. I'm going to put in 1/2 of the 1/2 of the height. Okay, and I'm going to multiply that by the width, which in this case is the base. So all I did was I took this area formula here and I just replaced. We know that the width is equal to the base, so I put the base. Okay, so this, let's make that red. And that comes from here, which is red. Okay, and then the length gets replaced by half the height right here. I'm going to make that orange, and I'll make this orange. Okay? So then you know exactly where the area of the triangle came from. All right. So I'm going to call this equivalence from triangle to rectangle. Right, and I'm going to add it to this. So you have full reference to it.
Okay, thank you.
Okay. There we go, right there. Okay. All right. So now we're going to go take a look at the next one. The next one is rhombus to the rectangle. Do I have rhombus to the rectangle? I don't. Let's go to YouTube real quick and see if we can find something. rhombus to rectangle. It's amazing what you can find on YouTube. Everything is there. Let's see, that didn't include this. Let's say Montessori rhombus to rectangle. Then we have parallelogram. No, it's not here. Okay, so that's fine. Let's go to the next one. And you'll see they're really all the same. So I think once you see a few of the lessons, you'll be able to easily apply it. So let's go to equivalence of a parallelogram.
This lesson is showing the equivalence between a parallelogram and a rectangle. And this is inset number 5. Step 1, we'll name the figures. This is a parallelogram. This is a rectangle. Step 2, we'll show the equivalence between these figures sensorially.
You need me to rewind a little bit? I know you're writing and watching at the same time.
No, I got it.
The pieces of the rectangle fill the frame of the parallelogram, and that shows that they are equivalent sensorially.
That's brilliant.
Yeah.
Step 3, we'll name the lines in the figures. This is a parallelogram. This is its base. And to show the height of the parallelogram, we need to see a perpendicular line from the base to the opposite side. So either of those lines shows us the height of the parallelogram.
Is that really a perpendicular? I guess so. Didn't look like it.
It doesn't look
It's a
perpendicular.
rectangle. This is its base.
It could just be the angle, though.
Yeah.
Base of the parallelogram. Height of the parallelogram. Base of the rectangle, height of the rectangle. And step 4, we'll make a statement about their equivalence based on the lines in these figures. The base of the parallelogram is equal to the base of the rectangle. And the height of the parallelogram is equal to the height of the rectangle. Their base and their height are equal. We can also make a statement about the equivalence of the rectangle to the parallelogram. A rectangle is equivalent to a parallelogram when the base of the rectangle is equal to the base of the parallelogram and the height of the rectangle is equal to the height of the parallelogram. Once again, when students have seen this presentation, they can trace the insets in their geometry notebooks, label the significant lines in each of the figures, and write a statement of equivalence from parallelogram to rectangle and then from rectangle to parallelogram. It's also important to note for this material that this parallelogram is also a rhombus, but for this lesson, we'll be referring to it as a parallelogram.
Okay, that's where the rhombus one went.
Okay.
Okay, so let's go back then to our, yeah,
Miriam's in the waiting room.
thank you. I don't see her. Oh, there she is. Okay, so let's go back to our document. All right, and I'm going to change this to equivalences. Okay.
Hello, good morning.
Hi, how are
Sorry
you
about that.
doing?
Morning.
I'm good. I'm on my way into school, so sorry about the
Okay, no
delay.
problem. Okay, so now let's take a look at the formula for the parallelogram or the rhombus. It'll be the same. Okay, so again, the area of a rectangle equals length times width. Now we know that the base of the parallelogram is equal to the width of the rectangle, right? And we also know that the height of the parallelogram is equal to the length of the rectangle. So we can come up with the area of parallelogram by simply replacing length with height and width with base. Okay? So I'm going to use color coding. This goes with this, right? And this comes from, let's pick a pretty color. Okay.
Mm-hmm.
All right. She said that she would have them trace the figures and note the important lines. I would do more than that. I would have them trace the figures and cut one of them so that they can actually rearrange it on their own. And then they can paste it into their notebook. They would write all the equations, label all the things on the actual figures that they paste. So they would label the base of the parallelogram, the length, the width, everything. All right.
Monica, this might be for another time, but for their like notebooks or geometry things, do you kind of model the expectations of what a follow-up work should look like at the beginning of the year?
Yeah, you could do that. That would be fine.
Okay.
That's totally fine. Eventually they'll catch, I mean, they're pretty good at knowing, kind of what
I
you're
guess
asking.
that's my question is kind of do they know if you say to
Yeah, I mean, I
cut and
think,
glue and
look,
label?
yeah, if you're working with the fourth graders, I would say that you might want to, get them used to the standard of quality of work that we expect in upper elementary. It might be different from lower elementary. Every piece of work must have a title. Every piece of work must be dated. The writing has to be done neatly, so you might want to set the standards by showing and modeling.
Yeah, okay.
Probably with the older children, you won't need to do as much of that.
Yeah, okay.
I would recommend having a separate geometry notebook, which would be similar to the math notebook, the quadrille paper.
Okay.
Last year we didn't have a separate one, and what happens is that the geometry curriculum gets all spread out and you don't see the nice progression because it doesn't have its own notebook. And when you're showing work to parents, you want to be able to tell a story of what they've been doing.
Yeah, no, I always used to use my science notebooks for conferences because it just speaks for itself. So,
absolutely, but the
yeah.
same thing will be with math and geometry, especially because it's so visual.
Yeah.
All right, so now we're going to look at trapezoid and rectangle. Hopefully I have that. Do I have a trapezoid? No, I have parallelogram twice. We're going to quickly look. We're going to quickly look for trapezoid. Let's see if we have it. Montessori trapezoid. I doubt they have it, otherwise I would have found it. No. Okay, but I think you get the idea.
I'm just turning off my video for a minute because I'm walking into school, so I'll be back in like 2 minutes.
Okay. All right, so.
And Monica, would you do this like one lesson at a time?
Oh yeah, one at a time.
Yeah.
Totally. Yeah. And you could actually challenge, if you've got some students that are, really sharp, which you will.
Yeah.
You could challenge them to find the other, go ahead and find the area for the trapezoid and see how that works
Right.
for you.
Mm-hmm.
That would be a really fun thing for them to do. Okay. All right. All right, so I want actually to write down, you'll see this in the album when you look, but there's a statement here for the trapezoid, which kind of summarizes the findings, and you could try it on your own when you are in school and you have the thing with you. Mm-hmm. So the statement reads as following. It says, a trapezoid is equivalent to a rectangle having as its base the sum of the bases of the trapezoid and a height that is 1/2 the height of the trapezoid. The height of the trapezoid. Okay, so if I remember correctly, the area of a trapezoid equals 1/2 the base. 1/2 the base, let's say 1/2 times the base times the sum of the heights divided by 2. H1 plus H2. No, I have this backwards. It's the height, it's the bases that are different. So it's the height times base 1 plus base 2. Okay?
Okay.
All right. Okay. So next, after those, come the decagon, which is really cool because it gets you closer to the circle, the area of a circle. Okay, it's very similar to the area of a circle, which we'll also see. All right, decagon and rectangle.
This series of lessons will be to show the equivalence of a regular polygon to a rectangle. And for this series, we'll use insets number 11, number 12, number 13, number 14, number 15, and number 16. We'll start this presentation by looking at these two insets. This is a regular pentagon.
Regular has been defined in lower elementary as an equilateral, equiangular polygon. So they have supposedly done work with regular and irregular, okay?
Okay.
And the way they show regularity is by, you'll see her do it, by moving the inset around, showing that it fits any which way you do it because it's equilateral.
We call it a regular pentagon because it has 5 sides and all of its sides are equal. That's what makes it regular. And this regular pentagon with 5 equal sides is equivalent to the whole regular pentagon. This divided regular pentagon is divided into 5 equal triangles. Base of each of the triangles is equal to the side of the regular pentagon. So for right now, we'll put these pentagons aside and move on to another regular polygon. So this is another regular polygon. This is a decagon, a regular decagon. A decagon has 10 sides, and a regular decagon has 10 equal sides. And I can prove that by rotating the decagon in its frame. This regular decagon is equivalent to the whole regular decagon. It also has 10 equal sides. And as we saw with the pentagon, it's divided into 10 equal triangles. Each of these triangles has as its base the same length as the side of the decagon. So this is another regular polygon. This is inset number 15, and it's a rectangle. It's made up of a whole rectangle, which fills 1/2 of the frame, and a rectangle that's divided into triangles, which fill up the other half of the frame. So inset number 15 shows us 2 rectangles, a whole rectangle and a rectangle that's divided into triangles.
Monica, can you let Miriam back in?
Oh yeah, thank you. Okay, I think we're all back.
This is step 2, showing the sensorial equivalence between the decagon and the rectangle.
So I don't think she made it clear enough that the half rectangle that's in triangles, that's actually equal to the decagon.
Okay.
She didn't make that clear enough. And that's where you get you'll see when we get to the formulas, you get 1/2 the perimeter, because it takes 2 rectangles to kind of show this. All right, let's keep going. Maybe she'll show it now, I don't know.
So these are all the pieces that made up this rectangle.
Oh, I guess she's going to show it
And
now.
here are the 10 triangles that made up this decagon. I'm taking the pieces from the rectangle
Ta-da!
and here I show that they fit into the frame of the decagon. I can take the pieces from the decagon and show that they fill the frame of the rectangle.
So just to make a point, when you're presenting this to students, this one I would actually do for them. I don't think that I would, pass it around.
Yeah.
It's a little more complicated. I would do it for them, but then I would stop and say, okay, so what do you think this means in terms of writing a formula for the area of a decagon? And that piece you can elicit from the students by asking appropriate questions, okay?
Look right here. I have to exchange one of the triangles for the equivalent triangle divided into 2 pieces. The pieces of the decagon fill the frame of the rectangle. The pieces of the rectangle fill the frame of the decagon. They're equivalent figures. And the whole rectangle from this inset is equivalent to the divided rectangle from this inset and the divided decagon. So we'll continue to look at the sensorial equivalence of these figures. I'll take the whole decagon and the pieces of the divided rectangle so we see that there are 2 regular decagons filled up. And now, so the whole rectangle's frame is filled by the pieces of 2 whole regular decagons, 2 whole regular polygons. This is step 3. I'll name the lines of these figures. So on the regular decagon, the regular polygon, there is this line all the way around the figure, which is called the perimeter. It's the sum of all the bases of these triangles. That's the perimeter.
So just so you know, in lower elementary, they have a lesson called Parts of a Polygon.
Mm-hmm.
So at that point, they define the perimeter. They will also define the apothem, apothem, which is basically the radius. It's from the center to one of its vertices, the apothem. Okay? So that is something that they'll need review on, but they've already theoretically have seen in lower elementary. I never knew the word apothem until I took my training. Never heard of it.
I never heard that one either.
but it's a real thing. I looked it up. Whenever I saw a term I didn't recognize, because I'm a chemie, and I thought, you know, I had a lot of math, and if I didn't,
Right.
if I haven't heard it, I'm not sure it's real. So I would look it up, and it's real. Okay.
This is the base of one of these triangles. And then the line that goes from the midpoint of the base of the triangle to the center of the figure is called the apothem. This line shows the apothem, that distance. On the rectangle, if we look at the divided rectangle here, this is the base of that rectangle. And this distance is the height of the rectangle. We can also see it here. So on the rectangle, we have its base and its height. And on the decagon, we have its perimeter, its side, and the apothem. Step 4, we'll make a statement of the equivalence of the lines in these figures. So let's look again at the perimeter of the decagon and see if we can find its equivalence to a line on the rectangle. This line is the base of the rectangle, and it's equivalent to half the perimeter of the decagon, of the regular polygon. So half the perimeter of the polygon is equal to the base of the rectangle. Remember this line, this distance called the apothem on the polygon? We can see here that the apothem of the polygon is equal to the height of the rectangle. Here's the height of the rectangle. Here's that distance called the apothem on the polygon. So we see that the base of the rectangle is equal to half the perimeter of the polygon, and the height of the rectangle is equal to the apothem of the polygon.
Okay, that's as far as she takes it. So we are going to go back to our document here. All right, now so now we're looking at regular decagon. Actually, it turns out to be for any regular polygon. Okay. So the statement in the album is the regular decagon is equivalent to the rectangle with a base of 1/2 the perimeter of the decagon and the apothem. And the apothem for its height. Okay. So if we look at the formulas, again, the area of a rectangle is equal to, I like to say length times width. I don't like the way she's saying base times height. I think it's confusing, but that's just me. So the area of a regular decagon is going to be equal 1/2 the perimeter, 1/2 times the perimeter times the aperture. So it's the rectangle with 1/2 the perimeter. Okay, and that's going to be in yellow. And the apothegm, oh, this is yellow right here. Oh, this is so pretty. And the apothegm for its height, we'll make that light blue, and the apothegm for its height. Okay? Sense?
Yeah, Monica, my only question is in the insets, the rectangle that she has, you're really just looking at half of the rectangle.
Right, which is why, so she, yeah, so I agree with you. She didn't make that quite clear. I thought you could have arrived at the conclusion much quicker than she did
Okay.
by just showing, look what happened. We had to use 2 rectangles to make this thing, which means we need to take half of the perimeter. So there's an easier,
Right.
way to get to with the way she got to it.
Yeah, okay.
Absolutely, I agree with you. All right. So I think the next one is, and just know that this applies, let me just say here, regular decagon or any regular polygon. And you could do the same thing with she never went back to the pentagon.
Right.
You could do the same thing with the pentagon or any regular. Okay. All right, let me see if I think I have a few more videos I wanted you to see. So we saw that. That's actually a whole different thing. Okay, so the circle one, so that's it for equivalence.
Okay.
So as you can see, let me try to unshare. I'm ready to stop sharing. How do I do that? Oh, there we are. Okay, so you can see that I would call this, the series of lessons we just saw, as one of the core parts of the upper elementary geometry that you want to get to.
Okay.
All right. So you can see that's quite a few weeks of lessons.
Yeah.
Probably a couple of months, which is why I said you're not going to get to all the constructed triangle lessons.
So you really don't think geometry is actually taught once a week?
No, it is. It is. I was being a bit cynical when I said
Okay, okay.
no, it is. They managed it last year and they were really good about it.
Yeah.
We'll see how things work this year.
Right, no, of course.
I'm concerned about the shorter day. I'm concerned about having to double up on lessons because of distancing.
Right.
I know how tight the schedule has always been without those things. And, geometry is just one of those things, that seems to be, lower on the list than other things.
Right.
You're not going to cut out lit circle. You're going to cut out geometry before you cut out lit circle. You're going to cut out geometry before you cut out math. Yeah. Right? Or history or science. So.
Yeah, I'm thinking about it in terms of weeks. And if each of those lessons is like 1 week, that kind of takes me through 1 month of lessons.
Exactly.
I know we have holidays and things, but
Right. And
Lital,
yeah.
Lital, you can also think of it like I started working with Upper L in January, and between January and March, we literally did no geometry over the entire spring. There was
Okay.
none. Unless Eliza did it with the girls, but the boys had no geometry.
I see. Okay.
So, like unless she did it private lessons, but between January and March, I think I remember Eliza doing maybe 3 lessons between those 3 months, and I think she did 2 in February.
Okay.
With each grade, but that
No, it's good for
it.
me to kind of get a sense of how, like,
Yeah.
ideally, and then what actually happens. Yeah.
So so in reality, instead of the schedule, you could tell the kids that like they have geometry, but really they didn't have Ivrit yesterday because they missed it, or they had to do Chumash instead. So we're
Okay.
gonna skip geometry and we're gonna try throwing it in at some point in time, but we never
Okay.
actually do. So
Okay.
yeah.
No, okay. I gotcha.
Yeah.
Thank you,
Yeah,
Michaela.
it's really sad. It's really sad.
it's just one of those things that, with the
Mhm.
dual curriculum, and now, so there's always been pressure on the general studies program. I have found I had to be really assertive about maintaining that 50-50 split.
Yeah.
I would literally count the hours and the half hours and the 15 minutes, and I would write them down and show it
Right.
to my partner, my co-teachers, and everybody's really good about working with that, but you kind of have to be assertive about that. I know that Rivki truly believes that as much as Judaics is so important, it's also really important to have the high quality academics. So
Yeah.
so I
I mean,
always
the other thing is if we don't have enough material to give to the parents by November, like the kids, like especially just math and geometry in general, like we're gonna have to like up it up.
right.
Like just the week before even.
Yeah. Okay. So all right. So now we're ready to move on to the study of area for real. So this was really showing equivalences and
Right.
coming up with formulas. Now we're going to do it again. And I think that although these lessons are also important, I think if you had to cut some lessons out, it might be some of these, because they are a repetition of what you've done with the insets, the metal insets. This uses a different material called the area materials, and they're just not as fun, I don't think.
Okay.
All right. Okay. So, okay. So, I start this. I start this set of lessons with a story. It goes something like this. Long ago, there was a farmer who was getting old, and he felt it was important to think about how the farm was going to be run after he was too old to manage it, or after he was gone. And the farmer had 3 children. 2 of them were boys, and 1 was a daughter. I have here, the boys were called Strong Hands and Strong Arms, and the daughter was called Marigold. Okay, so he thought, so I have 3 children. I have to put 1 child in charge. Which one will it be? Should I just give it to the oldest son, which is what's usually expected? But he felt, no, I really want to give it to, I want to kind of put a test out there and see what my children come up with, and whoever wins the test, or, will be chosen. So he said, okay, I'm going to see if there's a child that can figure out how big my farm is. And the child that can figure that out will be the one that inherits the leadership of the farm. So, so one of the sons came up with, I really need to show you the materials for this. Hold on a second. I have it here. Yeah. So one of the children, one of the sons, came up with, he took the farm and he drew some lines. And he said, so the farm is if you draw lines in this direction, it's 1, 2, 3, 4, 5 lines wide. And the father was like, well, that's very nice, but that only tells me really maybe how long it is. It doesn't really tell me the whole picture. So the next day, the other son came and said, well, really what we need to do is we need to draw the lines in this direction and say that the farm is that big, right? As many of the lines as we have. I think there's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the farmer was like, well, I'm not sure that also tells the whole story. So finally it was Marigold's turn, and she came up with something a little different. She said, well, Dad, what I would do is I would draw the lines in both directions and come up with something like this. Now, these materials are these thick yellow wooden blocks. You'll see them in the classroom. You'll see them in the videos. So she said, in order to measure how big the farm is, we really need to measure how big it is in this direction and how big it is in this direction. And of course, she came up with the right answer, which was the area of the farm. And she's the one that got the leadership. Of course, led to all sorts of other problems because of our misogynistic world. But that's a story we're not going to tell.
For another time.
We'll save that for another time. Okay. So I'm going to show you now the videos for this material. This material is called the area material, the yellow area material. Okay. You okay, or do we need a break?
I'm okay.
All right. Okay, so again, I'm going to share the screen. And we are going to, there we go, area lessons.
This lesson is on finding the area of a rectangle. We'll start with the beginning.
Now, I've seen arguments for these area materials coming before the insets. Okay, and I'm okay with that. If I think either order works, I don't have a problem with that. So just putting it out there.
Which is how we use a square to measure surface. So this is a rectangle. If I wanted to measure its surface, how could I do that? Let's think. Well, one of the things I need to do is figure out what my unit of measurement is.
And you know, I would say actually even further, it shows up afterwards in the album, and the album actually says that this work is a consequence of the work done with the metal insets. I would say that these set of lessons you could give to fourth graders and then have them do the metal insets in fifth grade. You'll see what you think after you start working with the materials. I've done it both ways, so you decide. You know, if you need some lessons for fourth grade, this might be a good way to do it.
So I am going to adopt a unit of measurement, and that's this distance. This is a length. And my question is, how long is this rectangle? So I'll use my measurement. There's 1 unit, 2 units, 3 units, 4 units, 5 units, 6 units, 7 units, 8 units, 9 units, 10 units. I could say it's 10 units long. And then what about this length? Let's see. How wide is it? 1 unit, 2 units, 3 units, 4 units, 5 units. 5 units wide. That helps, but maybe not so much. So now I have a rectangle with these units of measurements marked on it, which helps me see that I have 10 units long and 5 units wide, but I still can't quite say what the measurement of this surface is. So let's extend these units. So now I have this rectangle, which is divided into 5 parts. It's not enough to say that this rectangle is 5. So let's continue to look at the surface and its measurement. Here's a rectangle that's divided into 10 parts. So here we can see that measurement of 10 as one of the sides of the rectangle. So it's not enough, though, to say this rectangle is 10 parts. I need a way of describing the whole surface of it. Here is a rectangle, my same rectangle, divided into 10 units along this side and 5 units along this side. And now when I look at it, I can see that it has square units on the rectangle, and those square units cover the whole surface. And that's what I'm going to use to describe the measurement of the surface of this rectangle. It has how many square units? Well, there are 10 units on this side and 5 units on this side. 10 taken 5 times is 50. So the measurement of this rectangle is 50 square units. How do I know that? Because the squares cover the whole surface of the rectangle. So when I'm measuring surface, I will use square units as my measurement. So remember we looked at using a square to measure the surface of a rectangle? I've made some labels to express those numbers that we established. So this side, the base of the rectangle, has a measurement of 10 units. And this side, the height of the rectangle, has a measurement of 5 units. So let's take this information and make it into an equation. 10 times 5,
So
or
you see
10
how
taken
this is
5
really
times,
a fourth grade lesson, right?
equals
I'm not sure why
50
it shows
square
up
units.
later in the album.
So we can see that the surface here, the 50 square units, that's how we got the answer. What is the measurement of this surface? So 10 represents the base, the measurement of the base of the rectangle, and I can shorten the word with the letter B. B stands for base. And 5 represents the height of the rectangle, and I can represent that with the letter H. So base times height equals area of the rectangle. And this is called a formula. So if I have the base of the rectangle and I know the height of the rectangle, together they can give me the area of that rectangle. I can multiply base times height equals area. I want to show you something really interesting about this rectangle. We know this rectangle really well. Its area is 50 square units. But what if I turned it this way? Now the base of the rectangle is 5, and the height of the rectangle is 10. And if we use our formula, base times height equals area, what will we find out? 5 taken 10 times equals 50 square units.
So they know commutative property. They learned that in lower elementary, so that hopefully she'll tie that into here. It's just the commutative property of multiplication.
So whether the rectangle is oriented this way or this way, I can always find its area by multiplying those distances, base times height. And the surface is measured in square units. This is called a formula. So here's the formula. Area equals base times height, or base times height equals area. I have a new situation here where I have the area of this rectangle, the surface area, which is 50 square units, and I know the base of the rectangle, which is 10, but I don't know the height. So how could I find the answer to what is the height of this rectangle if I have this information? Well, let's take a quick look at the answer. What is the height? We know it's 5 from our work previously. So how can I get 5 as an answer to a problem that has 50 and 10 as its parts? So how do I find the height if I know the area and the base? Well, I need to take the area, which is 50, and divide it by the base, which is...
So this is a really good lesson that I actually end up doing something very similar to this when I introduce the idea of inverse operations to solve for variables when they get to pre-algebra. So this is actually a really cool kind of introduction to the idea of inverse operations, which becomes so important later on.
10, and that's how I can get the answer 5. Let's look at that as a formula. The height equals the area divided by the base. Here's another formula. This one we can use to find the height of the rectangle.
So I really like that. I think that's awesome. But again, I see it as a fourth grade lesson. That's just my opinion.
Mm-hmm.
So you'll decide, you'll know what to do. Okay. So the next thing is the area of a parallelogram using this yellow area material.
This lesson is on finding the area of a parallelogram. So here's a parallelogram, and we already know from our work with rectangles that if we can count the squares on a figure, we can find the measurement of the surface of that figure measured in square units. And this parallelogram has been divided, and
so one other thing that I do for fourth grade to introduce area is if you want to do some fun stuff. So this idea that you count the squares, I think right here I might do where they do either a tracing of their hand on graph paper or their foot on graph paper. Hand is more interesting because if they spread their fingers out, you have a lot more breaks in the drawing. And then kind of pose to them the question, now what am I going to do? I can't really count the squares, right? Because it's not all the squares are complete. So they can maybe estimate what the area is, you know. So the other thing I've done is I've had them with clay, I've had them make a fried egg. I have them make the white of the egg, I smush it in, they make a flat white pancake. And then they put a yellow glob in the middle on top of graph paper. And again, how are we going to find the area of this? So those are kind of cool things to do at this point, to think about, well, what happens when you can't count the squares?
there are squares in it, but there are also squares that are incomplete. So I can't really count the squares on this parallelogram as it is. So I'm going to bring in another parallelogram exactly like it. But this parallelogram is divided into two parts. So I just want to confirm with you that these two parallelograms are exactly the same. And then I'll use this parallelogram to find its area. So first of all, let's look at the lines on the parallelogram that we can identify. This is the base of the parallelogram, and I'm going to label it B for base. And the height of the parallelogram is any one of these vertical lines. So I'll put my label H for height right here. What I've done
Did you see what
is
she
made
just
this
did?
parallelogram into a
She moved
rectangle.
the.
Yeah, okay.
And when it's a rectangle, all the squares within it are complete. So I can count or multiply to find the surface area of this rectangle. But this rectangle used to be a parallelogram. How did the lines on the rectangle compare to the lines on the parallelogram they came from? Well, let's see. This labeled the base of the parallelogram. Now it labels the base of the rectangle. They're exactly the same. And this labeled the height of the parallelogram, and now it labels the height of the rectangle. So they're exactly the same. So if I multiply the base of the parallelogram times the height of the parallelogram, it would be the same as if I had multiplied the base of the rectangle times the height of the rectangle.
So this is really important because what children want to do is they want to multiply the base and then they want to go up here and measure this and multiply that. And that's not the right answer, right? Because it's not, that's not the right, what you really want is the height, which would be this, okay?
Rectangle. And that, I know, can give me the measurement of the surface area of the figure, in this case, the parallelogram, in square units. So base times height equals area. And just one more thing. Remember, I showed you that we no longer needed to use the x as a representation of the multiplication sign. We could use this dot, which we understand now means times. Well, we can simplify this even further by just putting these two variables together. When mathematicians and students see two variables right next to each other with no symbol between them, that says multiplication. So
this is really also very good. Obviously, you'd have to, any terms that you use, you have to have defined. So she's used two terms already. She's used variables and she's used surface area, two things which we haven't defined. So just make sure that if you're going to use any terminology that it's been previously defined.
BH means B times H, and that gives us the formula for finding the area of a parallelogram.
Okay. All right, so that's really good. Lots of value there. Okay, so let's see what else we have. Parallelogram. Okay, let's look at the triangle.
Hey guys, how are you today? So today we're going to continue with our study of area, and today we're going to learn how to measure the area of the figure that I have here on my table. What figure is this? It's a triangle. And what kind of triangle do I have? Well, let's look at the angles. And all of the angles are acute, so it's an acute angle triangle. Today we're going to learn to measure the area of a triangle. Now remember, when you measure the area of a rectangle, all you have to do is count up all of the squares that are on the surface. But are we going to be able to measure the triangle's area that way? No, because if you look carefully, there's lots of squares on the triangle that are incomplete. And if I have incomplete squares on my surface, then I can't just count them all up. But let's see how we are going to be able to measure the area of this triangle. Let me show you what I have. Here I have another acute triangle. And if you look at it, it's an equivalent triangle because it has exactly the same area. I'm going to use these two equivalent triangles to help me find the area of my triangle. I'm going to double the area of my triangle to make a square. Now that I've doubled my triangle, I have a square. And I can measure the area of a square by counting up the squares on the surface. Or I can do it an easier way by multiplying the squares along the base with the squares along the height. So here I have 10 multiplied by 10, which is 100 square units. That's the area of my square. But remember, my square has double the area of my triangle. So I have to take those 100 square units and divide them by 2. And 100 divided by 2 is 50. The area of my triangle is 50 square units. So the first way that we can find the area of a triangle is multiplying the base times the height and dividing it by 2. Base multiplied by height divided by 2 gives us the area of a triangle. But guess what, everyone? There's another way that I can find the area of my triangle. So once again, I have my acute angle triangle, and it's equivalent to this acute angle triangle. Okay? So another way that I can find the area of my triangle is by multiplying the base by half of the height. So I'm going to cut my triangle in half, and I'm going to rearrange it like a rectangle. So now I have my base, which is 10 squares.
All right, so in a way, I can see why this is considered more abstract than the metal insets, because as you see, we've lost the triangle, right? So she's
Right.
rearranged it, but we don't have a visual of the triangle like we do with the metal insets. So that would be one argument for doing this later.
Okay.
Okay.
And I multiply it by my height, which is now 5 squares because I'm taking half of my height. And that gives me 50 square units. So another way to find the area of a triangle is multiplying base times half of the height. And that will give me the area of my triangle. So half of the height multiplied by the base gives me the area of a triangle. Half of height multiplied by base equals the area of a triangle. But guess what, everyone? There's even another way to find the area of a triangle.
Oh, her voice is
So
really
once
annoying.
again, I have my acute angle triangle, and it's equivalent to this one. And this time, what I'm going to do is I'm going to multiply half of my base. So I'm going to bisect my triangle at half of the base, and I'm going to multiply it by the height. So I've cut my triangle at half of the base and I multiply by the height. So now I have a base of 5 and I multiply it by a height of 10, which gives me 50 square units. So another way to find the area of a triangle is by multiplying half of the base by the height. Half of the base times the height gives me the area of a triangle. Half of base times height equals the area of a triangle. And that's another way that you can find the area of a triangle. So those are the 3 ways that we can find the area of a triangle. Have a great day, everyone.
Okay, so we're going to take a little break. Let me just stop sharing here. All right, it's 11:37. Let's say we come back at, let's come back at noon, okay?
Okay. Mhm.
All right.
Thank you.
Yeah.
Thank you.
You're welcome.
Thank you, Monica.
You're welcome. Still here, look at that. Look at All right, I'm resuming the recording. Okay, so we were working on the yellow area material. We're going to get back to that.
Okay.
All right. All right. So we saw the presentations for the rectangle and the parallelogram and for the acute triangle. There is also lessons for the there's a lesson for the isosceles triangle, for the right triangle, and the obtuse triangle. Okay, so the material lends itself to all those presentations. It also lends itself to the area of the rhombus. Let's see what else we have on our videos. I may not have them all. Okay, so I have the area of a triangle and then I have area of a triangle 2. Let's look at that and see if there's anything new there. All right, I'm not sure, I don't remember exactly.
Hi, today we're going to look at another formula for area of a triangle. I want to do a quick review of the first formula that we used, and so I'm going to move the camera down.
Okay, so I'm going to stop this because she's still working on the acute triangle, and we saw all 3 formulas. So that's fine. So I don't think I have videos for the other area formula for the, the isosceles triangle and the right triangle, but I think you get the idea.
Sorry, aren't the formulas ultimately the same?
They are. They just show it for different triangles.
Okay.
And you don't have to do all the lessons. You can just do one. And
Okay.
frankly, you don't even need to do all 3 formulas that she did because they're all the same anyway.
Same too, yeah.
It just seemed to me too repetitive. Just do it once and you're done.
Yeah.
Okay. I have some other pictures here. Oh yeah, so I shared with you, oh, I wonder if I could turn that around. I see everybody turning their heads. That's so cute. I don't think there's a way to turn this around, but I'll figure it out. I'll make myself a note. So this actually shows you, let's see, turn around triangles. It shows you the derivation for the right-angled triangle, which again comes up with the same formula. And this one is also upside down. No, this actually doesn't belong. Well, that's the same thing we saw with the pentagon before. Anyway, I'll turn these around for you. And they're just, for you to be able to.
If you download it, you should be able to like open it as a picture and rotate it, or not.
All right, I'll work on it. Let's see what this is. Oh, an irregular polygon. This could be interesting. Let's see what this is.
Looks like 6 is my perimeter.
Oh wait, let me
6 is my
start.
length.
Let me start over.
Hello, kids. Welcome to a presentation on the area of irregular polygons. So polygons like this piece here, regular polygons have all the sides are the same and all the angles are the same. So we've got 5 sides on this pentagon and all the angles on the inside are the same. So that is a regular polygon. Guess what? Not doing that. Doing these guys. How am I going to find the area of these irregular polygons that I constructed? Okay, this is a lot of fun doing this. So how am I going to do this? Well, it comes down to that old saying, how do you eat an elephant? One bite at a time. So I'm going to set aside 2 of my friends over here, and I'm going to work on this irregular polygon. So notice it kind of looks like a cat's head. What am I going to do to find the area of this thing? Well, guess what? I'm going to flip it over and show you what I did. What you do is you take your irregular polygon shape and you turn it into shapes that you know. What do you know? Well, I know that right there I have a square, and I know that I have two triangles. So what I'm going to do to find the area of this irregular polygon is I'm going to find the area of the big square and the two triangles and then add them up, and that will be the area of my irregular polygon. So what did I do to do this, and how am I going to do this? Well, what I need to do is I need to have at least a ruler and a pencil or a marker to figure this out. And obviously I made this out of construction paper. When you guys do your follow-ups, you can make them out of regular paper, whatever. And you can also print out shapes at home. I've got shapes here that I've been tracing, but what you can do is at home, you can print out shapes and use them. But I've got to get back to work here. Sorry, distracted. All right, how do I find the area of this irregular? Let's start with the square. So I'm going to measure the sides in centimeters.
So this is a really good measuring lesson, Latal.
Mm-hmm.
And this is 7 centimeters on one side. So I'm going to break this down into parts that I understand. 30. My square, 7. Let me double check to make sure that all the sides are 7 centimeters. Yes. 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 So 7. We know that base times height is the area of a quadrilateral. So 7 times 7 gives me the area of this part is 49 centimeters squared. So I just took the square and I broke it down into parts of I took the shape, broke it down into parts of understanding. The square is 7 centimeters times 7 centimeters, base times height, quadrilateral, 49 centimeters squared. But I still have the triangles left to do. So what's my area formula for a triangle? That is 1/2 base times height. I'm going to put that over here to remind me, and I'm going to go ahead and measure my base and my height here. Okay. Looks like my base is 5 centimeters. And my height, now how do I find my height? Well, in order to find the height, I've got to make sure that I find the midpoint here and draw it to the other vertex. So I'm going to have 2.5 centimeters.
So just so you know, they've had lessons in lower elementary on altitudes of triangles and how to find them. It involves using the triangles from the geometric cabinet, and they use plumb lines to find the exact vertical. You know what a plumb line is? It's a weighted, it's just a string with a weight at the bottom so that it points.
I watched the video, yeah.
Oh, okay. So that's good.
And I have to draw a line to my vertex. Okay. And if you look closely, you can see the line that I drew there. Now I have to measure that line because that's my height. That line is 4.5 centimeters.
All right, let's move on to the next.
Apothem to vertex, from all of the apothems to all the vertex, intersect there at the midpoint, and with a pair of sunglasses on it, kind of cool. And this is the irregular polygon, but what I did was I went ahead and I broke it down into its constituent parts. And I actually learned something today. If you look at one of those pentagons there, one of them has the apothems to vertex, to the opposite vertex drawn. And I found out that if you have a shape with an odd number of sides, the apothem to vertex from all of the apothems to all the vertex intersect there at the midpoint. And if you look at the other side, I tried doing the vertices and it gave me a star. And then I realized that that doesn't work. So when you have a shape with an odd number of sides, you use the apothem to other vertex, and you do that, and you go ahead and you find the midpoint there. It doesn't work with the vertices on a polygon with an odd number of sides. I figured that out literally just like 15 minutes ago. I was like, oh, that's interesting. So I used that because what do I need the apothem for? I need the apothem to find the area of a regular polygon. And when I look at this, besides seeing this sunglass dude, I see two pentagons and a right triangle. So what I'm going to do is break it down into its constituent parts. Yeah, this looks intimidating, but this does not. It's kind of weird, actually. All right, so let's go ahead and get started.
So this is actually really cool to do because this is exactly what they're asked to do when they get to pre-algebra. You know, they give them these weird shapes and you have to draw lines. You've seen those kind of problems. You have to draw lines to identify the area of different shapes that you might know. Okay, let's see what this one's about.
My irregular polygon, my final one. This looks kind of like I don't know what this is. It looks like a cat, maybe. Maybe like Pikachu or something. I don't know. But once I flip it over, what do I have? I have a square and two triangles, and how many shapes did I set this out? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a decagon, has 10 sides, and I've got two triangles, like look like two isosceles triangles, and I have a square. So let's start with the square first. The squares are easier, just base times height.
All right, we get the idea, yeah?
Mm-hmm.
Okay. All right.
Monica, in geometry, do students practice the calculations of these things or just kind of working with the shapes?
They just work with the shapes.
Okay.
Yeah, they don't really do that, the practicing until they get to pre-algebra.
Okay.
So I do have them as a follow-up. I have them for all these lessons. I have them cut out the materials. So I would, in this case, I would use yellow construction paper and have them, you know, fold or draw the lines, right? So that they're kind of redoing the presentation. I would have them do 2 of them and then break one up to make the whatever shape they're making, the triangle, the rhombus, whatever, or the parallelogram. Okay. Okay. All right, so stop sharing. Oh no, I don't want to stop sharing. I want to look at the schedule. Okay.
Yeah, I had a question about the schedule. There's no Wednesday.
I know that's because I haven't changed the whole thing. So let's adjust this. So we're really doing well. We're way ahead of schedule. We're still almost a full day ahead of schedule. So we're going to make this Wednesday. And Wednesday, are we doing 10 to 1 again?
Yes.
Okay. 10 to 1. You know, I'm going to say, well, we'll say to 1 and we'll see how that goes. So actually we've done all this. So let me do this. This is Wednesday. This will be Thursday. And Thursday we're doing 9 to noon, yeah?
Yeah.
Okay. Good. So today's Tuesday.
Yes.
So we are, okay, so this is actually not Thursday. This is going to be, this is is going to be, this is all Tuesday. This is going to be Wednesday. So I think we're going to quit early today. And tomorrow we will do, we'll continue with the area of a circle. And then we'll do all the sum of the interior angles formulas. Okay, I just want to see where we are in the album here. Okay. Irregular polygons. All right. There's actually a different presentation in the album for irregular polygons, which is interesting. You can take a look at it. We did all this, and this. Okay. Yeah, so tomorrow we'll do our circle lessons, and we will also do, oh, I forgot to put tessellations in here, which is really fun. Tessellations. We're going to make this Thursday for now, and then we'll see how we're doing. I have a list of additional things I want to show you, but we may end on Thursday, depending on how it goes. And some of the interior angles. I just want to make sure I'm not missing anything. And then we move on to volume. Okay. Okay, this is really fun. Okay. All right. So that's what it looks like right now. Any questions?
I have two questions. Sorry. Are these, it seems we've done a lot of fourth and fifth grade. Are we moving into kind of sixth grade stuff, or?
Yeah. Yeah. So area is mostly fifth grade.
Yeah.
And circle is probably also fifth grade.
Okay.
The sixth grade curriculum is mostly volume.
Is volume. Okay.
So actually, I'm going to add something. It's volume, and I also want to look at surface area, which is something we haven't talked about too much. So when we look at the geometric solids, Thursday we'll take a look at surface area, all right?
Okay.
So yeah, sixth grade is mostly going to be surface area, the geometric solids, and volume formulas. Okay.
Okay. That makes sense.
Yeah.
Yeah, just to kind of see like the big picture of how it's connected.
Yeah. Yeah.
Yeah, and then Friday, I just had an appointment scheduled for 10:30 on Friday. So if we need time, I could do like an hour and a half on Friday. But
I think
just
we're gonna be done on Thursday, Tal. I really do.
Okay.
I think I'll be able to show you most of what you need by then.
Okay.
All right. Okay. Anybody else? Questions?
Monica, I just want to